Carlos Simpson, technically from Nice, but now from Princeton, and he will give a talk on some Fukaya categories of singular Lagrangians with coefficients. Carlos, please.
Okay, so thank you very much. It's good to be back in Kansas, should I say? I think I visited Kansas when I was 5 years old or something like that. Anyway, but I would like to come and visit in person if possible, but sometime. Anyway, okay, so thank you very much, Jan, for the invitation to speak in the seminar. So I hope what I'll be able to talk about will be interesting to people. Let's see now. Okay. Okay, so what I'd like to talk about is joint work with Fabian Haiden and Ludmil Katzarkov. I should have said joint work in progress. So we don't have any proofs really written down of the stuff I'm going to say. So pretty much everything in the talk is at least a pre-theorem, if not just a conjecture or a hope or something like that. But I'm hoping that this is we're sort of settling in on how the theory is supposed to work, at least in our particular case. So I'm hoping that this is pretty accurate in terms of how that should work in the end. And so this is also, we were working on this with Pranav Pandit for quite some time, and a long time ago with Alex Knoll also on this type of question. And so we'd like to thank Pranav for his contributions to the project. He's not currently working on it now, but he made lots of contributions. So what have we been doing? So we've been trying to understand the role of spectral networks in the S-n products of the Hitchin and Riemann-Hilbert correspondences. So that's WKB theory, and we wrote a paper in Communications Math Physics about that. And the more recent project is about the role in the notion of stability conditions on the A side of mirror symmetry. Now, so the question for the A side was to try to generalize the Bridgeland-Smith construction for higher rank spectral curves. So let me not go over the Bridgeland-Smith construction except to say that it's basically doing what we're doing here, except for the case where the spectral curve has degree 2 over the base, or we're looking at bundles of rank 2 and so on. And so, okay, well, unfortunately, we haven't really gotten too far in all of these studies. And another thing which I would like to know more about, but I'm sure Jan knows lots about this, and many of you do, but it's the relationship between these two directions. So the direction of the WKB type of appearance of spectral networks, and the current thing about stability conditions on categories with Fukaya categories with coefficients. So, and well, we suspect, of course, I mean, everybody suspects, I think, that this, whatever relationship there is between these two sides should fit into the Kontsevich-Soibel wall crossing picture. But as yet, I mean, I don't know what to say about that. I would like to, but don't. So today I'll be reporting on our current work that we've been doing for some time now with Ludmil and Fabian. So what's the setting? So we're going to take a Riemann surface. The Riemann surface is just going to be the complex plane, but some of the stuff we say, I guess, will work for a Riemann surface. And we fix a finite subset of endpoints, so it's sort of a pointed Riemann surface, or a pair. And we fix a symplectic form on X, which just means a volume form. We'll assume that one is chosen, although, as we'll see a little bit later, the thing that we're really asking for is the data of areas of regions. So I think you could specify any area of a region, or you could even make a more general kind of a ring where you include those things as parameters. So any curve, by this I mean a one-dimensional curve, I'm sorry. So any one-dimensional curve inside X is a Lagrangian. And we'll be thinking about singular Lagrangians, which are graphs embedded into X. And we'd also like to work with a coefficient system. So what is a coefficient system? Roughly speaking, this is going to be a locally constant sheaf of pre-triangulated A infinity categories over an open subset. Here by open, I mean Zariski open, on the other hand, subset. and there might be some singular behavior at a collection of singularities. So the terminology here is the terminology of perverse Schober in Karpanov, Sheckman, Soibelman, Sukhanov, and other people's terminology. It's supposed to be the categorification of the notion of a perverse sheaf. Although I think some of the things I'll say, like what's at the bottom of this page, for example, would even be that you don't need to have a perverse sheaf. You could just have a constructible sheaf, and you could categorify in the same way the notion of constructible sheaf. Okay, so a certain part of this theory is devoted to discussing the notion of singularities of such sheaves of coefficient sheaves of categories. But in the present situation, we're not going to be discussing singularities because we don't know how to do that. And the base is just a complex plane also, so there's no fundamental group either, or higher homotopy. So our local coefficient system is not going to have any monodromy. And so we can really think of D as being just a fixed constant fiber category. In fact, in what we prove, it's almost the easiest possible one after a vect, which is the A2 category, the representations of the A2 quiver, in fact. But it's good to think a little bit about the general case, at least to guide what we're going to be doing. So for example, so we're going to be imposing kind of in an ad hoc way an endpoint condition over the subset P, where the graphs are allowed to sort of stop at the points of P. But I'm pretty sure we didn't work this out. But I'm pretty sure that should be interpretable in some way as having some kind of constructible sheaf of coefficients where we extend the constant sheaf by 0 at the points of P in some way. So I think that the case of having just like if you take homology of a curve with coefficients in a sheaf that has an extension by 0, that's going to be the same as relative homology of the curve relative to the set of points. So this should be the categorification of that observation. Okay, now we'd like to consider Lagrangians with coefficients in D. Now, if we take the Novikov ring and take the residue field, then this is going to be the case of looking at sections of the perverse Schober over the graph in the sense of this paper, which maybe Jan can comment on this, but it's apparently still in preparation by Dikerhoff, Karpanov, Sheckman, Soibelman.
Yeah, I mean, we decided to sort of to split it. There will be several papers because in its kind of natural generality, it will heavily rely on this Lurie formalism of infinity categories. So then kind of it will be not just one paper, but several of them.
Okay. Anyway, yeah. So I'm sure that what I'll say here will probably be contained in that and all that stuff anyway, as we'll see as we go along. But anyway, but I mean, okay. So now the simplest local singularity of the graph. So by this here I mean a local singularity of the graph inside the curve, inside our smooth curve, is going to be a triple vertex. And in that case, this is kind of well known, I think, folklorically at least. The condition of being a section means that we have a triple of objects, the objects over the 3 edges, that should then fit into an exact triangle of the fiber category D. Okay. And as we'll see below, the technical meaning of this is that we should have an A infinity functor from the A2 category. So by A2, that means the A2 quiver representation category, which is just the case of, I mean, it's the category of representations of a quiver with a single arrow. Okay. But if you have a single arrow inside a pre-triangulated category, then you actually get 3 objects. You have the source, the target, and the cone, and those fit into a triangle. So a representation from A2 into a category is basically the same thing as a triangle. And that was something that we discussed at length and Fabian explained to us. Okay, so now we'll actually be assuming that D is represented by a DG category. You can take your A infinity category and make an equivalent DG category. And we're going to assume that the underlying additive category has direct sums. And in that case, you can actually interpret the data of a triangle as being the data of a strict triangle in D. So this is I think I commented about this in previous talks on a little bit. This is, I think, an interesting point which people may not necessarily be familiar with, which is an exact triangle is not an actual exact triangle in a pre-triangulated DG category. It's not just giving those 3 maps. It's actually giving 6 maps, which is to say the 3 maps F0, F1, F2, plus the homotopy saying that the compositions are equal to 0. And then there's a condition which says that, in the strict version of the condition, it says that the sum, there's 3 different sums you can make out of those things. And those 3 sums should all of them be the identity of those 3 objects, okay? So this is an inhomogeneous condition. So you can't just forget about the maps or set the maps to equal 0 or something like that, because this is an inhomogeneous condition. Then in the case of an A infinity functor from A2 into D, you can, if you have this strict data, then that's going to define an A infinity functor, but where the higher stuff is 0, kind of a strictified A infinity functor. But you could have a more general sort of A infinity functor that's not strict, but it's still going to have in some way some inhomogeneous term. Basically because, I mean, the minimal model for the A2 category is a category that has an M3 term, which is the identity, and that's sort of the same. It's the same identity that shows up. We'll see this in the picture later in the talk. Okay, so now here's, let's just draw a typical picture. So here's a graph. Then we've decorated the graph by objects of our category. And at each of these vertices, in fact, it's the same because I'm drawing here on a spectral network. At each of these vertices, we should have an exact triangle, okay? A mapping to B, mapping to C, and then mapping to A of 1. I'm not going to explain this today, but there's a thing about orientations which is extremely confusing to me. So an edge should sort of have an orientation, which is a lift of its tangent vector into the universal cover of the circle bundle of the tangent bundle. And if you change that by 180 degrees, in other words, by pi, then that's equivalent to doing a shift in the fiber category of 1. So in particular, if you go all the way around, it's a shift by 2. Okay, if you do a 360-degree turn, that's a shift by 2 in the fiber category. So that's why once you've gone around A to B, B to C, and C back to A again, if you think about what's going on here, this is actually a map to A of 1. You might think of
these objects are in the coefficient category D.
Sorry?
The objects ABCDs,
Yeah, they're in the fiber category D, yes.
In the D, okay. That's also the coefficient category. So
that's the coefficient category, yeah. Sometimes I call it the fiber category, and sometimes I call it the coefficient category.
Okay.
Okay, so. Okay, if you had a more general multiple point of the graph, then you would consider, I mean, if you had an n-fold vertex, you would consider functors from an-1, the quiver category an-1 into D. So one way of looking at that is to actually, you could take the multiple vertex and sort of decompose it into a bunch of trivalent vertices, and then just put exact triangles at the trivalent vertices. Then the kind of the miracle in this subject, so I'm kind of guessing here, but I think this is what's called, what Kontsevich calls the symplectic geometry of triangulated categories. The sort of miracle in this thing is that all this stuff actually works out. So I mean, there's a whole bunch of notation and shifts and all that kind of thing that I'm not talking about at all. But the amazing thing is that they all actually work out correctly, and after all, you just sort of forget about verifying them because it always works. I mean, but I mean, that's something which is completely not obvious at all to start off with. You know, why would it be the case that the different ways of, say, I mean, there, for example, a 4-valent vertex, there's several different ways of making it into 2 different trivalent vertices. Why would the data of triangles and so on, you know, so you'd have 2 triangles in several different ways. Why would all those data be sort of equivalent? You know, a priori doesn't seem obvious at all, but anyway, that's the relationship between symplectic geometry and triangulated categories. Anyway, but so these functors are going to be incorporated in an automatic way into our general definition. Now we'd like to define an A infinity category over the Novikov ring. The Novikov ring, so we fix the ground field little k. I think it's arbitrary, maybe characteristic 0, but I'm not sure that matters. So when we define a ring which is k adjoin all the positive real powers of some variable t, okay? Power is greater than or equal to 0. Of course, t to the 0 is equal to 1 here, okay? And we'll call that ring R. I'm not sure what, maybe I'm using maybe not good notation or something, but anyway, we'll call that R. So there's a maximal ideal with which is just all the strictly positive powers of t, and the residue field is k, the quotient. So we have I guess the only thing that needs to be the Novikov covering is basically behaves a lot like a discrete valuation ring. But there are some things which aren't true. So for example, the fact that the maximal ideal is finitely generated, that's not going to be the case here. So you can't choose a uniformizing parameter, and you choose this parameter t, but of course, the square root of t is t to the 1/2. You can sort of extract arbitrarily many roots of t plus real coefficients. Anyway, so that's the Novikov ring. So that's the ring which always appears in symplectic geometry for the reason which we'll see in a minute. And its fraction field is called the Novikov field, and that's what people usually in symplectic geometers usually use as their coefficients for the Fukaya theory. Now, as I said, our sheaf of categories D should actually be a sort of a sheaf of categories with singularities and so on, and they should actually be A infinity categories over the ring R. And I'm not completely sure that I really master exactly how that definition should work, but they should clearly be defined over R. On the other hand, for what we're going to do here, we're just going to, especially since the category is even rigid, it's not even going to have any deformations. But anyway, we're going to assume that D is constant in the R direction. That's to say that it's given by taking a pre-triangulated A infinity category over the ground field, little k, and then just tensoring with R. When you tensor, if you have to be a little careful when you take, if we're working in the world of pre-triangulated A infinity categories, if you tensor, it might not be pre-triangulated anymore because you might not have added you'll add new morphisms, but you wouldn't have the cones on those morphisms. So you need to complete in some way. And that's but that completion is kind of going to be intrinsic in what we do because we're going to be taking twisted complexes anyway. So now the main information that we would like to incorporate is the information of disk corrections. So that's supposed to be, we're in a two real dimensional or one complex dimensional symplectic manifold. So disks are just basically regions in the curve. So that's why I can work on this subject. It's not all that difficult, at least in that direction. And these corrections are supposed to provide a deformation of the A infinity structure of the category of sections over the graph starting out over K. I put a star here because I'm assuming that probably Jan can maybe comment on this. I'm sure probably you guys are also going to have the disk corrections. I don't think, as far as I understand, at least as far as anybody who I talked to knew how to do it, we didn't have the definition with the disk corrections as an input of our construction.
Carlos, will your logic be like constructing Maurer-Cartan element which deforms some undeformed category?
Roughly speaking, I guess I'm going to be thinking of it as just defining some operations called MK, in the A infinity structure.
Yeah. Yeah. So that's
But they'll have coefficients which are t to the power a, where a is the area of some disk, basically.
Yeah.
Anyway, so that's what we need to do. If you guys had done this like 10 years ago, we would have just used your definition and we would have been able to work on other things, right? But anyway.
It will take another 10 years just to write it down. So.
Yeah, so we're just sort of doing a quick and dirty version of that, I guess, for our purposes here, is maybe what you could say. Okay, so anyway, so we need a suitable definitional framework for these things. Because this deformed category is the thing on which we're going to be trying to prove the theorem. Okay, so now let me start. So I'd like to describe the definition. That's one of the main things I wanted to do in the talk today. So I'd like to describe the definition. So I'm going to give a sort of a preliminary attempt to the definition to start with because it's a little bit easier. Plus I understand it better. And then we'll discuss the sort of the augmentation of that definition. Which is mostly due to Fabian. This is also mostly due to Fabian, but we'll discuss the augmentation of that in a minute. But so let's start with the preliminary attempt at this definition. But as you're going to see, it's not completely great, and we have to choose some extra data. So that's why we would rather have a more intrinsic formulation. But let's start with the choosing extra data version. So we fix in any case, we're going to fix an embedded graph inside X with endpoints at the vertices P. So, but what does this mean by endpoints? It means that the only places on the graph that have valency 1 vertices, in other words, an edge that just stops, that's only allowed to happen at the point P, okay? At some point of the subset P. And another thing is that all of the interactions of the graph with that subset P are, in theory, supposed to take place on just a single edge. So you should really think of, if you have like 3 edges meeting at P, you should actually think of having like a 4-valent vertex and then an extra edge that then hits that point of P.
Carlos, your set of endpoints, is it fixed forever, or you?
Fixed forever, yeah.
So your singular Lagrangians will have fixed endpoints, yeah.
I'll have fixed endpoints, yeah. Well, you'll see in a minute that's not completely true, but yeah.
Okay. All right.
Yeah, and in fact, in our case, it's the 6 points of a regular hexagon. So it's not very minimal. Anyway, but I mean that we can make the definitions, I think, in a more general setting. But we're going to suppose that the PIs are arrayed along a circle. I'm not sure how crucial all this is, but maybe important for some things. We're going to assume that the points are arrayed around the edges of a circle, and then we're going to assume that the graph is the edges of the graph are always in the interior of the disk. I mean, any compact subset would do the trick. And if you think about it, the modifications of the graph that you might do in order to get to special Lagrangian representatives, they're not going to move edges out of some convex subset. Okay, so we can think of everything as happening inside a disk, basically. Now, what we're going to do to make the definition is we would like to change this graph into something where it doesn't have vertices, okay? Because we actually know how to define the Fukaya category of just smooth objects, and having a decoration of an object of the fiber category or of the coefficient category on a smooth curve is not going to be a big problem, okay? So the idea is to decompose the graph into a collection of strands, which are simple curves joining pairs of points of P. So we declare that we should choose a maximal collection of non-intersecting strands that's in a ribbon neighborhood of the graph, and that they should not generate regions of area 0. And so, I mean, if you draw some pictures, you'll see that you can make a maximal thing like that, and they're not unique in it. That choice of strands is not unique in any way, but it's going to have the same. I mean, supposedly going to have the same Fukaya category. Okay, so and so I should also say that, I mean, we're moving the strands into a ribbon neighborhood of the graph G, but we're actually declaring the area to be 0, and we're sort of declaring the symplectic form to be 0 inside that ribbon neighborhood, in the sense that changing the strands a little bit is not supposed to change the areas of regions. So the areas of regions, you might say, they're defined by the symplectic form, by integrating the symplectic form over the regions of the actual graph G. But then those are just sort of assigned to the topological regions that are cut out by the graph. The topological regions cut out by the graph are also the same as the topological regions cut out by the strand. Okay. Now we've transformed the graph into a union of just usual smooth Lagrangians. We can just take the Fukaya category of these Lagrangians, and we need a wrapping condition at the boundary points. So here's a picture of the strand. So I tried to draw. So these are supposed to be smooth. Of course, my drawing thing, I didn't make them smooth. There's a little corner there. But think of these strands as being smooth things. The ribbon neighborhood of the graph. The graph is a graph with a hexagon and 6 spokes. The purple things, those are the endpoints, or 6 points of P. And so the ribbon neighborhood of the graph is in green. And then you just choose some strands which are not supposed to intersect except at the boundary points. And they sort of go parallel. You might have several strands going parallel along a given edge or not. And if I'm not mistaken, I think I managed to choose a maximal collection of strands with the property that it doesn't have area 0 region. So if you think about it a little bit, suppose can you guys see my arrow?
Yes.
Yeah. Okay. So suppose we add a new strand that goes from this vertex over to this vertex, right? If we added that, then we would create an area 0 region, right? Because this strand plus this one, those are the boundary of a triangle that's going to have area 0 if we declare the area inside the green region to be 0. So this thing is supposed to be a maximal collection, and as you can, I drew sort of topologically what it is up here. You can see there's the loop, which is the hexagon. So this region here is going to get the area, which is the area of the hexagon, and then topologically there's just 2 extra edges that go from here to here, and here to here. Okay. So that's the picture of, so that's the idea of choosing strands. Now, what about the wrapping condition? So, I mean, if I go back here, so here we have, for example, a vertex with 1, 2, 3, 4 edges coming into it, okay? So now we have to, that's going to induce some notion of morphisms between these strands, and that's going to be given by a wrapping condition. So the wrapping condition, this is kind of ad hoc on my part because I'm not sure I know the exact correct terminology in the symplectic geometry viewpoint. We'll give it a try in just a minute. But so the wrapping condition, it says that each edge is wrapped to the left as we go towards the point. Okay, so as it comes into the point, it's supposed to wrap like that. Then you're supposed to wrap the edges kind of in a certain order. So it's the rightmost edge that wraps first and then successively, so that they should intersect. We'll see in a picture in a minute. And so I think, if I'm not mistaken, if I understood Vivek's talks and so on, is that one way of saying that is that we're looking at a stopped Fukaya category where there's a boundary, which is the circle. We have our boundary points are on a circle. That we put a stop right just counterclockwise of each vertex, okay, along the circle. And then the wrapping picture gives us a notion of morphism between the edges. So, okay, so now I drew the picture. I tried to draw the picture of the strands and the wrapping. So this is a picture where the vertex is in purple. There's 3 strands coming into the vertex. We put a stop over here and we wrap from the vertex in the direction of the stop. So we first wrap. So the first edge, that's this one, that's the rightmost edge. That's the kind of the first one, because that's going to be the source of all of our morphisms. So that gets wrapped the most. Then the second edge gets wrapped a little bit less, and then the third edge gets wrapped the least, okay? And so now you can see that's going to generate some intersections between these Lagrangians. And those intersections are the place that are supporting the wrapping morphism. So there's a wrapping morphism from the first to the second edge, that's F. There's a wrapping morphism from the second to the third edge, that's G. Then there's going to be a wrapping morphism from the first to the third edge, that's the one over here. And there's also going to be a disk correction for a disk of radius of area 0, right? Because this is all infinitesimally small. So there's this gray shaded region, that's a disk of area 0. And that's going to give us a disk correction. The disk correction is the M2 term, M2FG. So it just says that we have if we compose F and G, then we get a map from the first to the third strand. That's all that says. But you might notice that, so I tried to draw this, if I'm not mistaken, correctly in terms of what the disk corrections look like. So it's maybe good to also investigate this disk a little bit. So you see this disk, it has 3 vertices, but this first edge is actually considered as what we're calling a tail. So this first edge is kind of a tail that comes into the disk. Then in the disk morphism, there's an F and a G. And the composition of F and G, that results in a map from the tail into the last edge. Okay. So for some reason, I mean, you can see from the picture, that's the way it works, right? And you can see that gives you the correct composition operation. So that gives a good evidence that should be the way we should do things. Anyway, so that's the wrapping. Now, so what's our category? So our category is going to consist of strands decorated by objects of the fiber category. And in the morphism complexes, we include the morphism complexes of the fiber category. So every time we have a morphism, we also decorate those by morphisms of the fiber category. In particular, if I can go back in for a minute, the morphisms in the green circles, those are supposed to be decorated. I mean, each of these strands is supposed to be decorated with an object, and those morphism things are supposed to be decorated with a morphism between the objects inside D. And so we can actually just give a complete, this is the combinatorics is very simple here. We can give a completely algebraic description of the infinity category. It's actually a DG category. The infinity category, whose objects are the strands, okay? So in this algebraic setting, you can just write it down. It's not very difficult. There's just a wrapping morphism from any germ of a strand to any germ of a strand that's on your left as you go towards the point, okay? And then those wrapping morphisms are given coefficients. They're decorated by morphisms in D. And we just compose them by just composing them in the natural way at the point pi. They also compose a morphism, a wrapping morphism composes with an endomorphism of the object on each of the strands, the source strand and the target strand. On the other hand, the definition is just that that the compositions between strands the compositions of wrapping morphisms located at different points are equal to 0. And you can see if we go back to the picture, I mean, if we had another point over here, if you wrap a little bit these edges, they're not going to wrap enough to meet the other point. So there's not going to be any kind of disk of area 0 that relates the morphisms at different points. Okay. So the morphisms, the composition of wrapping morphisms at different points are just equal to 0. And if D was a DG category, and we're going to assume that that's the case, then this category of strands is also a DG category. And then we could, in principle, already include twisted complexes. However, before we do that, we first add the disk corrections, the large disk correction. Okay, now what's a disk? A disk is just an embedded disk whose boundary consists of some strands. So if I can go back in the picture. So in this picture, we're going to have a disk here with 1, 2, 3, 4 edges. Okay? I guess, yeah, I mean, that disk could also have a tail. Okay, so if we say we add this edge as a tail, then the first thing would be this guy, then this guy, then this guy, then this guy. I'm not sure. I may have said something slightly wrong here. Okay, now a disk is going to contribute a collection of terms that we'll denote M index K to the deformed A infinity structure. I'm not writing this down because I'm not necessarily very good at that, but you know what an A infinity category is something where you have morphism objects and morphism complexes, and then you have operations. M0 is probably 0 until we declare otherwise. M1 is the differential, M2 is the composition, and then we have M3, M4, M5, and so on, which are compositions of sequences of morphisms. Okay. And then we're going to define an MK term every time we have a disk, and these are going to enter with a coefficient of t to the power a, where t is the Novikov parameter and a is the area of the disk. I'm not completely sure if I may have made a mistake in what I wrote here in the last second paragraph. Anyway, I'm sorry if that's the case. But the degree of the multiplication operation is the number of boundary edges of the disk. And I'm not sure if it's -1 for a tail or not, but anyway, sorry about that. And anyway, so but in what follows, we're going to discuss, a disk is going to be called a polygon to emphasize the fact that it's a collection of strands. Now the inputs of the MK operation are going to be wrapping morphisms located at the vertices of the polygon. And there's 3 different types of terms. So one type has values which are endomorphisms of the object associated to one of the edges. So that means you compose the wrapping morphisms as you go around the disk, and that gives you an endomorphism of each of the edges. Then there's 2 other types of morphisms which are a little bit more complicated with where you have a tail. Well, let's not refer back to my picture, but I mean, a tail, you have an edge, and then you have another edge, and then some edges, and then they come back and meet the first edge. Then the first map in the first input map is the map from the input tail into the next edge of the thing, and so on. And then you have the maps of the input maps of the vertices of the polygon. Then when you compose all those together, you get an output map, which is a map from the input tail thing into the last edge of the polygon. Okay. And there's a similar thing on the other direction in output tail. But so actually, I mean, if you write down these things in terms of wrapping at each of the vertices, and then look for a disk just in the usual sense, you get the correct picture. That gives the correct picture, even if what I'm saying is not necessarily exactly correct. But you can just write down all the wrappings and just look for a global disk in the usual sense of the Fukaya category. Anyway, it's putting all these operations together gives us an A infinity structure. And the proof, I mean, we kind of wrote down the proof in a couple of times in some different cases, but essentially the proof is just the same proof as given by Haiden in his paper on Fukaya categories and higher genus surfaces. And actually, if you look at that paper, he doesn't really actually give the proof either, but he just sort of makes it clear why it's true. So anyway, so I mean, it's going to be it's supposed to be a bunch of cancellation of terms. I mean, the infinity axioms are some axioms on these operations, and a bunch of stuff has to cancel out basically. And once you start writing it down, you see that that's all going to cancel out. So that's really it's the same. I mean, that's his higher. Idea was for higher genus surfaces, but for I guess genus 0 surfaces, it must have been Paul Seidel or other people. Anyway, so it's just the same proof because of the fact that our strands are really just smooth curves. So they're just usual Lagrangians. The fact that the things are decorated doesn't change anything in the proof because the decoration maps are just sort of the logical, they go from the logical place to the logical place.
Carlos, may I ask you, because you kind of concentrate on technical details here, but kind of for the future of your talk. So since you mentioned Bridgeland and Smith anyway, so these trends should correspond to for example of strands are geodesics of the quadratic differential joining two zeros of the quadratic differential in their picture, and you kind of building Fukaya category which should correspond to three-dimensional spheres projected to these segments. How should I think about?
Yeah, so I'm going to discuss that in a little while, but I do see that I'm getting a little behind on the talk, so maybe I should skip.
Okay. Sorry,
but
yeah.
Let me just go back to the picture and say that, so the statement here is that this green thing, that's supposed to be a Gaioto-Marnitsky spectral network. Because we're talking about the case of...
Yeah, but these purple things, they are what?
The purple things are those are the edge points, but the strands...
No, the purple points. The purple points. Are they zeros of the quadratic differential, or are they poles?
Well, they could be, yeah.
Okay.
But the strands themselves, as you can see, they don't really go in the same angle because if you want to choose those guys, I mean, that's kind of why we have the other definition. Let me just, yeah, sorry, I should be going a little faster now. Anyway, so what do we do? Let me just be a little faster. What do we once we construct the infinity structure, then we add twisted objects. So that means pairs consisting of an object plus a Moore-Cartan element. The Moore-Cartan condition is just written in the usual way. And then we just, by the general formalism, we get an A infinity structure. Okay? You just need to get an A infinity structure on the simple objects, which are just the decorated edges themselves. Maybe, but let me just skip over this. There's the condition that we gave on, I mean, the definition of the wrapping morphisms, those are allowed to have Moore-Cartan elements, which are, you might say, two-sided, in the sense that there's no nilpotency condition on the Moore-Cartan coefficients at the wrapping points. And that's just because the wrapping morphisms themselves are nilpotent, right? Since after a while, if you compose them enough, you get to zero, okay? But then you would also include some kind of nilpotency condition on your Moore-Cartan elements, which are global over the edges themselves. Skip that. So this would give a construction of the category, but we're working on a second, better construction, which is a little bit suggested by your question, Jan, which is that the objects on the strands are not sort of in any immediate way equal to the objects over the edges of the graph. Roughly speaking, if you have an edge that has several different strands, then the object on the edge is going to be some sort of multiple cone of those objects on the strands. Okay, I was explaining. Well, you guys actually have the thing somewhere. So, well, so for example, if you have two strands that come together at a trigonal vertex and then run adjacently on the third edge, then you're going to have a morphism between the two objects of the strands, and on the third edge, that object is going to be the cone of that map. Okay. So we clearly don't want to deal with calculating this type of thing. So Fabian came up with a better idea. And in fact, I think he basically knew how to do this before. But anyway, the idea here is to look at, and so this is also your question, Jan. So now instead of asking our edges to end at endpoints of the picture, points of the subset P, now we just ask for floating edges, okay, which can end anywhere inside the surface. Okay. On the other hand, those edges are not supposed to correspond to objects of the category. So, so instead of having an A infinity category, we have a curved A infinity category, which includes these single edge objects, but it has an M0 term. Okay. There's a curvature, which is an M0 term. And for any floating edge, it has two pieces at each boundary point of the edge. Okay. Then we pretty much define the things the same way. Let me skip this a teeny bit. Let me just describe this picture. So, so we have the similar type of wrapping morphisms at all the interior vertices of the graph now, but there's no stop. So the wrapping can go around as much as it wants. And then we can write the picture. So we take the real blow up at that vertex. Then our wrapping morphisms are sort of represented by paths along the real blow up. So I just wanted to draw the picture of the paths that you would have in order to get the structure of a strict triangle that I was talking about at the beginning. So here's the structure of a strict triangle. It's a triple of objects A, B, and C. We have maps from A to B, B to C, and C to A of 1. And we also have homotopy. So those are maps from A to C, B to A of 1, and C to B of 1. And there's a homotopy condition that says like D of H0 is equal to F1 composed with F0. Okay, that says that they're homotopies. But there's also this inhomogeneous condition, which says that the sum H1 F0 plus F2 H1, that wasn't good. That should have been, sorry, I should have, no. H1 F0 plus, no, okay, F2, sorry, it's F2 H0, sorry, that's a 0 here. Excuse me, that's a 0. Anyway, but I drew these in starting with the edge A. I drew one of these terms in green, so that's go to here and then go to here. The other term is in purple, go to here and go to here. Okay. And the sum of those is supposed to be equal to the M0 term, which is the identity going once around the circle. Since when you turn 360 degrees, you have a shift of 2, the identity thing gives you a degree 2 term. Then the disk corrections are the same as before. Okay, so let me just not say that. And now the more Cartesian element for the curved category, just you add the M0 term at the start. But that sort of, as we saw in the previous slide, that just sort of automatically contains the condition of having an A infinity functor at each of the vertices.
Sorry, I don't quite get your definition for this floated edge. Can you illustrate what does that mean? Like what kind of objects, new objects you're considering?
Well, if we go back to this picture, instead of the strand, which goes from a boundary vertex to a boundary vertex, we might have a thing which is just this edge itself of the hexagon, for example. So it's not an object of the category, because edges that are objects of the category, they have to start and end on boundary vertices. But if we just take this edge, this edge of the hexagon, that's going to be a curved object.
Okay.
This is Fabian's idea, that you can define these curved objects. Each of those has an M0 term, and when you put everything together, you include wrapping morphisms at each of these vertices, and you put everything together, that gives you the same structure, basically.
Okay, thanks.
Anyway, yeah. Sorry, that was a little fast. Sorry about that. Let me just, so there's the notion of objects over the edges that you can get by pairing with a figure 8 object. But again, let me, as Jan suggested, let's go a little more quickly. Let me just give the statement. Sorry. The statement of the objects over the edges is that if we have an object of our category of twisted things over the graph, and if we have an edge of the graph, then let's let A be the minimum of the areas of the 2 regions that bound that edge, right? An edge always has 2 regions next to it, right? We take the minimal area of those 2 regions. And then the statement is that the value of our object over the edge G is a well-defined object in the category of sort of torsion objects, so to speak. I mean, the category, which is the fiber category tensored with R mod T to the AR. So it's not, so in other words, it's only well-defined up to T to the A. it's not defined, it's not well defined in all powers of t, but the first t to the a part of that object is well defined. And as a conclusion, in particular, it makes sense to project into the fiber category over the residue field, which is dk, because that's modulo any positive power of t. And then the statement, part of the statement is that these things that we get are going to fit together to form a section in the sense of dkss. That's you, Young. In the sense of yeah, dkss. So they define a section category of sections over the graph, okay, which is this category where you put a triangle at each vertex, but without the deformation terms. So you can always restrict to the graph, to the residue field, and get a section over the graph. So now let's give some notations. So we define our Fukaya category of objects over the graph on the pair XP with coefficients in D over the Novikov ring R, and it's the twisted objects of the objects which are just given by the edges. Or you could put strands here if you want. Then the global category is some type of direct limit over the graphs, which we don't really need to work with because we can just sort of choose a fixed big graph. But the global category is defined to be the direct limit over all the graphs. Or the direct limit is just including one graph in a bigger graph. I mean, now if we extend scalars to the residue field, then we obtain this thing, which is supposed to be the same as the section category. If we tensor with the residue field, we're supposed to get the same thing as the section category of the graph with coefficients in the fiber category. And if we extend scalars to the fraction field, then we're supposed to obtain the classical Fukaya category. And what's supposed to be true furthermore is that this Fukaya category is actually independent of the choice of graph, as long as it's sort of connected and meets all the vertices. And that's basically the point there is that if you move an edge of the graph, then you're actually changing the object by an object which is torsion with respect to the ring R. The torsion is pretty much the area of the region that you moved the edge along. And you can move any one graph to any other graph by these moves, where the difference between the two, I mean, an object on one and it's going to have a corresponding object on the other, and they're going to differ by torsion in the ring. So when you tensor with the fraction field, it's just the same. So anyway, the conclusion is we have a diagram of A infinity categories like this. So we have an A infinity category over the Novikov ring. Then this maps to the A infinity category over the field, over the Novikov field. And it also maps to the A infinity category over the, which is really a DG category, over the residue field. So I think it's good to cogitate for a second on this. Now we'd like to put into, I mean, why are we doing all this? Because Kontsevich proposed a Devisage program for symplectic fibrations. This was in his String Math 2016 talk, which I think is still maybe available on video possibly. I don't think, as far as I know, I don't think he wrote down this stuff anywhere. But the idea is that we're going to look at symplectic fibrations, and then we take symplectic forms on the total space, but where we make the area of the fibers go down to 0. Okay. And then in some kind of limiting sense, the section category is supposed to be the category we've defined is supposed to be some kind of limiting version of that Fukaya category of the total space, where the coefficient category is the family of Fukaya categories of the fibers. Basically. Now, one way that, so this is my closer to Jan's question. One way that this can show up is suppose we have a spectral curve. Okay. Then, so in the case of Bridgel and Smith, or also Fabian, Ludmil, and Maxime's paper too on the subject, in their case, the spectral curve was a degree 2 cover corresponding to a quadratic differential. And pretty much what we're trying to do here is treat the case maybe of degree 3 cover, for example. And so now we can get a symplectic fibration. One way of doing that is just to take the cotangent bundle of X itself as a symplectic manifold, but take that relative to the spectral curve itself. So we're looking at Lagrangians in the fibers that are graphs connecting points of the spectral curve. Right, Lagrangian, the total space Lagrangians are Lagrangians in total space with boundary along the spectral curve. And then a different way, and this is maybe what Jan was talking about, is that you could also take conic fibration over the cotangent bundle whose singular fibers occur along the spectral curve, then look at usual Lagrangians in that total space. And those will typically sort of be families of thimbles joining together two different points of the spectral curve. I mean, I never completely understood, you guys can ask Jan about this afterwards maybe, I never completely understood why you would actually want to do this, except I guess that it's a way of getting a CY3 category. But we formulate the notion of special Lagrangian. The notion of special Lagrangian is happening over the residue field. So we say the section, right? So what's an element of this category? Well, from what we said before, that's the same as the DKSS section category. It means on each edge of the graph, we have an object of fiber category. Then we have some data of triangles at the vertices and so on. So now we say that a section is going to be a special Lagrangian if the fiber object over the edge is semi-stable. Sorry, I should have said something. We're also given sorry, I skipped that slide. We're given a family of stability conditions of the fiber category with coefficients in the cotangent bundle of the base. Okay, so we ask that it be semi-stable, and also that the central charge of the fiber stability condition contracted with the tangent vector of the edge yields a point in the complex plane in the central charge plane that always has the same phase as we move along the edge. So in particular, if the spectral curve upstairs, as in the case we're looking at, is just a constant triple of sections given by a constant triple differential, then that's just going to say that the edges in the base are supposed to be straight, and it's going to tell the slope of the edge in the base with respect to the choice of the Lagrangian in the fiber. So this is, sorry, I skipped this. What the central charges in the family of stability conditions are supposed to take values in the cotangent bundle of the base. If we just integrate, you get the central charge of the total space. So let me just go to the picture. So there's a picture of of how you get spectral networks just from the picture of special Lagrangian. So let me just put this. Let me draw the picture here. So this picture is a picture. This is the base. This is our complex plane. The fiber. This is the cotangent bundle of the base, and the thing in heavy black. That's supposed. I mean, these things. That's the 3 points in the section that are sections of the spectral curve, which is we're assuming has degree 3, for example, over the base. Now you can make a special Lagrangian in the fiber by just taking a line segment joining 2 points of the spectral curve. Okay. So over this edge, we might take line segments joining 2 of the points. Over this edge, we might take line segments joining 2 different points, and over this edge, we take line segments joining 2 other points. And what's left over here is a triangle. So this triangle is not really a Lagrangian because it's actually contained in the symplectic fiber. But in the limiting situation, I mean, if epsilon is small but not equal to 0, that's going to be deformed to something which is a Lagrangian and which projects down to a very small little blue dot down here. And the area of this small blue dot is equal to the area of this triangle multiplied by the epsilon factor, which we're using to shrink the size of the fiber. Okay, and that's basically the picture of a Gayoto-Mornitsky collision point. And in this picture, well, if you know something about the A2 category viewed as the category as the Fukaya category of the complex plane with respect to 3 points, you'll see that this triangle here is really a quote exact triangle in that triangulated category. So I don't know if that's some kind of a joke or something like that. The fact that an exact triangle is actually a triangle, or was it maybe it was an unintended joke or something. Anyway, so that's collision. Let me just get to the statement here. Okay, so now the special Lagrangian objects are going to be supported on graphs that are Guyotto-Mornitsky spectral networks. And the objects that decorate the graphs on the edges are going to correspond to the Guyotto-Mornitsky data. So in their original work, they called that data just a pair of points of the spectral curve. But what we're saying here is that that should actually be considered as a special Lagrangian in the cotangent fiber, which is an edge a straight edge joining 2 points of the spectral curve. Now the conjecture, so I'm not sure, Jan, you can maybe comment on this, but I'm assuming this conjecture is probably due to Kontsevich. Anyway, it was Ludmil who told me the conjecture, who told us the conjecture. The conjecture is that there should be a stability condition on this Fukaya category over the capital K field that's characterized in the following way: that the semi-stable objects of a given slope are supposed to be the objects of this category, which admit liftings to an object ER over the ring, with the property that when you project the lifting into the Fukaya category over this residue field, that should have this special Lagrangian property. Okay. And why do we have this sort of lifting from capital K to capital R and then projecting down to little k? Well, the idea is that that's supposed to be in some way a notion of a special metric in the non-Archimedean setting. That's supposed to be a notion of a special metric on a stable object. And this special Lagrangian condition here is supposed to be some kind of analog of the Hermite-Einstein condition. Well, anyway, so what we're trying to do is just an extremely special case of this conjecture, which is the case where you have 6 vertices on a regular hexagon. The fiber category is the A2 category. And the family of stability conditions on the fiber category is also just constant, given by a cubic differential. And then we claim that the conjecture is true. Now, in this case, so this is sort of saying what, roughly speaking, the proof is, which is that the Fukaya category, remember I said this Fukaya category doesn't really depend on the graph. And if you choose as a graph just some edges that connect together the vertices in order, then you've got an A5 category, an A5 quiver. And so the full section category is just the A5 category tensor, the A2 category. And then Ueda showed that that this is actually equivalent to the B-side category of Z-mod 6 equivariant sheaves on the elliptic curve that has Z-mod 6 symmetry. That's also the same. The Deligne-Mumford-Stack quotient of the elliptic curve is also P1 with 3 orbifold points of order 2, 3, and 6. So you could also say sheaves on P1 with 3 orbifold points, 2, 3, and 6. So it showed that this category A5 tensor A2 is actually equivalent to this one. So we actually know a stability condition on that category. So of course, the big problem in proving the conjecture is that, the conjecture says there should be a stability condition. And of course, we know it's not easy to construct a stability condition. So you might say, what we're doing here, we're kind of cheating, so to speak, in the sense that we're using the fact that Ueda gave a B-side equivalent, which is something where we already know that there's a stability condition. So now we can work with the stability condition that we already have. The only problem becomes the problem of showing that the stable objects of a given slope are indeed represented by spectral networks. And to do that, we basically just calculate explicitly. And the principle of the calculation is that there are mutation operations which modify the slope. And they're given by, if you have a spherical, you can have a spherical object, which in the case of the elliptic curve is basically either a London or a skyscraper sheaf. And then you can do the operation of, if you have a spherical object, then you can send an object y to Hom from S into y, tensor S, then mapping to y, and then take the cone of that. So on the B side, that operation sort of transforms one slope to another, semi-stable objects of one slope to another. And on the A side, we can sort of say what that operation does. And so we end up with being able to write the pictures. So this is maybe looks a little bit complicated, this picture, but this picture is obtained by taking a small little object in the middle, then applying several times the mutations in one direction or the other. And so we can pretty much classify the mutations that you can apply and do an inductive argument that tells you that the mutations are invertible. So by undoing the mutations, you can always get back to a simple case when we just do the picture. So,
Carlos, can you go back to the theorem again for a second?
yeah. Yes.
Yeah. So it doesn't make sense to do it for A1, I guess.
Well, it does. The thing is, for A1, I should have said that the case of A1 is the Bridgeland-Smith case, actually.
Why is that?
I'm sorry, I should have said that. The theorem is pretty much known. I mean, maybe not in all general cases, but the conjecture is pretty much known in the case where the fiber category is A1. I mean, A1 just means vector spaces, the category of DG vector spaces, right?
Okay. Okay.
So in that case, there's really like no coefficient category.
Okay.
But you still have the spectral curve. And the Bridgeland-Smith, Haiden, Katzarkov, and Kontsevich theorem tells you exactly this conjecture. Yeah, sorry, I should have said that thing. It tells you exactly this conjecture in the case of A1 fiber.
Okay.
So I mean, we were trying to. I mean, the project was, of course, we thought we were going to do that quickly and then move on to higher things, right? But the project was to start looking at the case where the fiber category. I mean, maybe we just. I mean, probably somebody can do better than this, but anyway, the project was to look at the case where the fiber category has, corresponds to a spectral curve of rank 3 or higher, basically.
Okay.
I mean, we're hoping, of course, that some of the ideas showing up here are going to help. But as I said, our proof is sort of shortcutting the type of thing you need to do. And we thought about the type of thing you need to do, but we don't really have a proof of that yet, which is to try to make a minimization operation where you take a graph and sort of modify it to a new graph to sort of decrease some kind of energy and sort of do the analog of Hermite-Einstein discussion in this non-Archimedean case. We haven't been able so far to make that actually work. So, but we were able to state this theorem just due to the fact that Ueda already tells us what the category is and tells us that it has a stability condition. And furthermore, we can actually write down, as in this picture, the actual spectral networks. You can classify the spectral networks, and the classification is that they all pretty much look like this picture, so to speak, in a generalized way. And that those correspond exactly by induction to, I mean, the same inductive procedure for constructing all the semi-stable objects of all different slopes on the elliptic curve is going to be the same one, and the corresponding construction is going to also transform us between the different pictures for all different slopes, basically. So I just wanted to explain it just a teeny bit, just to end. If you look in the middle of this picture, you see a hexagonal vertex, right? And now let's draw that here. Okay, so if you take it as a hexagonal vertex like that, then you can do the mutation operations, and we'll get to a picture like this. I forget which operations they are, but maybe a few left and a few right mutations, basically. But now that middle picture, right? But see, the middle picture is also a hexagonal picture with vertices, but the vertices are these little vertices in the middle here, okay? Whereas this thing is, I mean, in this picture, the official vertices, so to speak, are these ones. So somehow or other, when you do these mutation things, that sort of shrinks down the sort of essential content of the object into a smaller and smaller little hexagon in the middle of the picture. But I just wanted to say that there's 3 possible types of pictures that you could put in the middle. There's this one. There's a spectral network which we've been using in our example, which is that middle vertex can sort of turn into a hexagon and expand a little bit. The spectral network condition basically says that the angles between the edges have to be 120 degrees. That's like the really rough sort of geometric picture. So if you write down a picture like that, that's going to be a spectral network if you decorate it appropriately. So that's the middle kind of picture, and the size of that hexagon can vary, and that gives us a parameter. And then as that size of that hexagon gets to be maximal, then it's not allowed to grow bigger than these points. And at this point, well, that same parameter actually can vary still some more, and it corresponds to a kind of a monodromy parameter as you go around. When that monodromy parameter is actually equal to 0, then this object can actually decompose into 6 different edges. Those 6 edges, that corresponds in some way to this degree 6 orbifold point. Sorry. Whereas here, there's 2 ways of decomposing this picture if you want. You can decompose it into a union of 3 straight lines. Or if you think about it, you can also decompose it into a union of 2 pictures, which are collisions. Sorry, I didn't draw that. But if you think of, there's a collision that looks like that with 120 degrees. Then there's another collision that looks like that, right? So if you take a direct sum of those 2 collisions, you would also get a picture like that. Those two decompositions, those correspond to the Z mod 2 and Z mod 3 orbifold points. Okay. Then let me just finish by, this is the picture of what you would get if in that initial type of picture, you started with one of these hexagons, and then you did some mutations. They're not the same mutations, but you did some mutations to the picture. You would get a picture like that, for example. So the pictorial conclusion here is that the spectral networks for this particular case all look something like this picture, basically. Anyway, so I'll stop here.
Okay, thank you very much. Questions? So basically, just to compare with this Bridgeland-Smith, when you have just a category of vector spaces in the fiber, they have a quiver with potential in the end, and this 3 Calabi-Yau category, it's kind of part of the pure algebra. But in your story, it's your 3 Calabi-Yau doesn't have this easy description, yeah? You still have a quiver with potential, but you should combine it with a fiber category, with this D.
I guess so, yeah. No, but the thing is, well, that's a complicated. I'm not completely sure I understand what you're saying, but I think I understand, which is that you can't turn this into a quiver picture. That's why this is more complicated, because the edges in a spectral network, they don't sort of decompose. I mean, if you have a quadratic differential, you can sort of choose. I mean, for example, if you take a quadratic differential and you look at a generic phase, then the endpoints are going to be always joined together by paths which are unidirectional with respect to the quadratic differential. Yeah. That's how they get the quiver. That's just not true in the
that's what I mean.
Which corresponds, as you know, I'm sure, Jan, that corresponds to the case that the WKB approximation question is more difficult in the rank, higher rank.
Yes. So then it's.
But I don't think that you can reduce this to like some kind of quiver type of construction. I mean, that's what we want to do at first, of course, but that's why you need to do this type of stuff that we're doing. I mean, and that's what I mean. To prove the theorem in general, you would have to take an arbitrary graph and have a procedure which sort of minimizes some kind of energy. You know, minimizes the default as to how far away you are from being a special Lagrangian. I mean, your edges might not go in the right direction and so on. You have to have a procedure that sort of minimizes until you get down to a picture like this, basically. This should be the result of the minimization process. But as I said, we don't have a minimization process like that. You can sort of see that, roughly speaking, it should exist, but there's you can't show. I mean, it's hard to show that it converges. I mean, it's hard to show that the minimization process doesn't sort of lead to a whole bunch of smaller and smaller hexagons or some kind of thing like that as you minimize.
Okay, more questions? All right, so probably everything is clear.
Well,
not
faster at the start,
yeah. Okay, Carlos, well then, thank you very much.
Okay.
Very nice talk, very interesting indeed. Okay, well then this is it for today.
Okay, so
Thank you.